Well, welcome everyone. My name is Erik van den Bom, and I'm a professor of mathematics in the Department of Mathematics of this university, Utrecht University. And my research specialization is the theory of Lie groups and connected subjects like representation theory, harmonic analysis, symmetric spaces. If you want to have more information about this, you can visit my personal website, which is easily found by just Googling on this name, and then everything will be clear. So on this personal website, there is also a page dedicated to this course where you can find all information about the course, like the topics that I'm going to lecture on each week. There are, but I think most of you will have done so already. So who didn't have a look at the website yet? Okay. So one of the things that is important of this website is that you will be able to download as a PDF the lecture notes for this course and the set of exercises. On the website you can also find explanation of how this course is going to be graded. And if I remember the details correctly, then I think that 40% of your grades will be determined by the grade for hand-in exercises. Oh, please, this course is video, and therefore we would like to keep these chairs free, but there are chairs available. But welcome to this course. So 40% of the grade will be determined by homework exercises, and I am in the very pleasant situation to have 3 assistants helping with the exercise class and with grading the exercises. I will introduce them to you during the exercise class. Okay, let's start with the course now. And of course, what I should first do is give a rough idea of what a Lie group is. Let's first give a list of examples of Lie groups. The group of invertible real n by n matrices is a Lie group. So examples of Lie groups. The group SLNR, the special linear group of matrices, invertible matrices with determinant 1 is a Lie group. Orthogonal group is a Lie group. Groups of Lorentz type are Lie groups. And for instance, the special orthogonal groups are Lie groups, and the unitary groups are Lie groups. The special unitary groups are examples of Lie groups. And as you know, these groups occur everywhere in mathematics, and some of these groups occur very often in physics. So it is important to have some kind of general theory of these groups, and this is what this course will be about. Now, how to characterize groups like these? Well, first of all, they are groups. But secondly, yeah?
Can you put a line in the middle?
That's a very good idea. Line in the middle?
No.
So then, I'm going to do a correction. So what is the general way to characterize these groups? Well, we'll see several characterizations, but the first is the more general characterization of a Lie group. A Lie group is a group structure, a group which also has a manifold structure, and there should be a compatibility with the smooth manifold structure and the group structure. So let's write down the definition. A Lie group is a group consists G with multiplication and an identity element, which at the same time is equipped with a manifold structure, equipped with a, let's say, a smooth manifold structure such that there's two maps which are important for this group structure. The first, of course, is the multiplication map from G times G to G, mu multiplication, mapping a pair x comma y to xy. By the way, is this visible for the back of the audience? Yes. It is? Thank you. I was thinking I'm going to ask to raise your hand if it isn't. So, but I'm happy that it is. And let's say I or iota, since I'm using a Greek letter here too, the inversion map, x goes to x inverse, these two maps should be smooth. Let's say, so I'll often abbreviate this as smooth. So this means in order to understand this definition, you need to know what a manifold is. And so there is a few things that you know about, basic things that you know about manifold theory. And you should have, so this is really a preliminary for this course, you should have seen this in an introductory course to differential geometry. But of course, if there is anything about differential geometry that I'm going to use, and you don't, you have a feeling that your background is not complete here, so please tell me in the break, and then we can see what we can do about this. A general remark, of course, is that you are all very welcome to ask questions. If something is unclear, if the notation is unclear or whatever, don't hesitate to ask. I would really like to be intelligible here. After all, that's the purpose of this course. So this is the definition of Lie group. And now you may wonder, well, I said the groups over there are examples of Lie groups. But this is not so easy to see. Why should those groups be manifolds? Right, there is something to do here. So one of the purposes of this first lecture is to describe a general result that will give, as a consequence, that those groups over there are Lie groups. The general result will not be proved today, but it will be proven at a later stage. Okay. Apart from, by the way, there is always the issue of a manifold being second countable or not. Second countable means that as topological space, the manifold should have a countable base of open neighborhoods. I'm assuming throughout this course that all manifolds are second countable, so have such a base. And the same thing, so in particular I'm assuming this for Lie groups. There is a delicate issue here that I am going to explain on an additional few pages of lecture notes. But I don't want to elaborate on that. This is really for those who love this kind of precision and axiomatics. Okay, let's list some other examples that are more clear immediately. If we look at Rn together with addition and 0, then this is an example of a Lie group. Why did I use plus and 0 here? Well, of course, because that's really the operation that I want to consider on Rn, vector addition. But in group theory, it is sometimes the custom to use plus for a commutative group operation and then use 0 for the neutral element. So, in particular, this is an example of a commutative Lie group. We could also take Cn, which of course in a natural way as a real vector space is isomorphic to R to the 2n. And as a Lie group, it's just R to the 2n with a plus and a 0. I'm talking here about real Lie groups. At a later stage, I'll say something about complex Lie groups. So every Lie group to be considered is, I'm talking here about the smooth category of real manifolds, after all. Another example, take R star together with, which is R minus the 0 element, together with the multiplication and together with 1. This subset is open in R, and therefore in particular it has a manifold structure. And it is of course completely clear that the group operation, multiplication, is differentiable of infinite order. So clearly this is a Lie group. Similar example, C star is C without the 0 elements. Multiplication and 1 is an example of a Lie group, and these two are commutative as well. So these are all commutative Lie groups. And now we could ask ourselves about general mechanisms of which of the Lie groups, these subgroups, homomorphisms, etc. Let's first start with the following observations. If G is a Lie group and H a subgroup, so let me be a Lie group and H a subgroup. If H is a smooth, so H is a particular subset of G, if H is a smooth submanifold, then H is a Lie group of its own right. With that manifold structure. So what's the idea here? So maybe you could take the chair and sit over there or something?
There's a spot over here.
Oh, there's still a spot over there.
Is there a chair over there?
Yeah. Well, this is a distortion of symmetry which I cannot handle with my Lie theoretic mind. So I'm doing it again. Okay, so the observation is that if you have a Lie group And the subgroup, and if this subgroup is a smooth submanifold, then it is automatically a Lie group. And so what is the reason for this? So what is the proof of this? Well, of course we have the group multiplication of G, which is a smooth map. This map is smooth. Now we also have the group multiplication for H, and of course what we would like to show is that this is a smooth map. So the question is whether this is smooth as well. It's not immediately clear. What does it mean that H is a subgroup of G? This means precisely that, so H is a subgroup, means precisely that the multiplication, this multiplication map is equal to the restriction of the multiplication map of G to H times H, and that it maps into H. And of course there is also a similar condition for the inversion map. But because H is a subgroup, one has this, and one has that mu G maps H times H into H. Now, from, let's call this 1 and let's call this 2, then from 1, it follows that mu H as a map from H times H, the restriction of this map to G, that this is a smooth map.
Doesn't 2 follow from this?
Oh, the question is whether 2 follows from yeah, so I've stated it a bit. You are right. Well, 2 really follows, I've specified this here already, right? So maybe I should write it, this causes confusion. I'll write it a bit differently. So, I'll write it a bit differently. So, so what we know is, so that mu G is smooth and H is a submanifold. This implies that the restriction of mu G to H times H is a map is a smooth map from H times H to G. The restriction of a smooth map to a submanifold is a smooth map on that submanifold. Right. Now, but we also know that this restriction, we also know that that because H is a subgroup, implies that the restriction, that mu G maps H times H into H. And now we know that if we have a smooth map, which maps into a smooth submanifold, then this map is smooth as a map into the submanifold. So H, a submanifold, now implies that the restriction of mu G as to H times H, as a map from H times H to H, is smooth. But this is mu H. So we've shown that mu H is smooth, and by a similar argument we show that the inversion map is smooth. So likewise, the inversion map of H is smooth. And this is basically the proof. Application, look at the circle group. It's a very simple application. Look at the circle group T consisting of complex numbers of modulus 1, so the unit circle in the complex plane. This is a subgroup of C star, and clearly it is a submanifold of C star as well, and therefore it's a Lie group of its own right. Another observation, which is easy to prove, is that if G1 and G2 are Lie groups, then it follows that the product group equipped with the product group structure and the product manifold structure is a Lie group as well. This is really an easy result, but it implies, for instance, that the p-dimensional torus, so consequence, the p-dimensional torus is a Lie group. So the Cartesian product of p copies of the circle with itself, viewed as a group and as a manifold, is a Lie group. Now all these Lie groups are connected. Commutative, sorry. And so you may wonder, is it possible to say anything about the collection of commutative Lie groups? And indeed it is, and this is the following theorem. We are going to, so what you will see is that in the theory of Lie groups, the idea is that many aspects of the group structure can be called in an infinitesimal way through the Lie algebra. The Lie algebra basically is the tangent space of the Lie group at the identity element, equipped with an additional structure, the Lie bracket. This is something that we are going to introduce during this course. And of course you cannot expect such a structure at the identity to say much about connected components of the Lie group that do not contain the identity element. So in some sense this is really going to be a theory of connected groups. And then the theorem is as follows. The following statements, so let G be a Lie group. And I'm assuming it to be connected. And the following statements are equivalent. Equivalent are the following statements. A, G is commutative. B, basically G is equal to the product of an RP and a TQ. So there exist integers P and Q, non-negative, such that G is isomorphic to T to the P times RQ. Now these obviously are very simple, connected, commutative Lie groups, and the theorem states that these are really all. So in other words, if you want to, the theory of commutative Lie groups is not very interesting, it's not very rich. Now, the proof of this theorem requires the development of some theory, so I'm postponing the proof to a later stage of this course. Let's turn to some non-commutative Lie groups, and you very well know that this matrix group of invertible matrix is not commutative. Multiplication of matrices is not commutative. This is not a commutative proof. This is not a commutative proof. This is not. So what you see is that these are typically examples of non-commutative Lie groups. And it is an interesting question as to what extent are they non-commutative. This is one of the questions that we will answer in the first lectures of this course. Let's first start with the general linear group. By the way, I'm sorry. I have used the notion of isomorphism here, but I haven't explained what it is. Well, it's quite obvious. But let's do it. Definition. It is very important. Definition. A homomorphism of Lie groups so a map phi from a Lie group G to a Lie group H is called a Lie group homomorphism. If the map, first of all, well, it should really preserve both structures. So it should both be a group homomorphism and a smooth map. Secondly, phi should be smooth. Now we also have an obvious notion of isomorphism. In phi is a Lie group isomorphism. If, first of all, it needs to be an isomorphism of groups, and so in particular this means that it should be a bijection. So let's require just that it is a bijection. Phi is a bijection. And then, of course, the inverse should be group homomorphism, and it should be smooth at the same time. In other words, it should be a Lie group homomorphism. So this is what an isomorphism is. So now I have really explained the contents of this theory. And of course, this is what an isomorphism should be, because it expresses precisely that the structures of the definition are matched. Okay. Let's turn our attention to the group GL and R. GL and R is the set of matrices, well, let's say X. Matrices n by n matrices with real entries, so square matrices with the property that they are invertible, or differently said, that the determinant is different from 0. Now, by the there is a question.
Yeah, I was wondering, there's also things that are manifolds and rings. Do we consider them as well?
No, we don't. Okay. The matrices that are invertible, clearly this is a group by the multiplicative property of the determinant and by the fact that the determinant of the identity matrix is 1. And so what's the neutral element here? The neutral element is just the identity matrix. And the multiplication map is matrix multiplication. But now, what's the other item of the other issue of the definition is that this should have a manifold structure. Why should this have a manifold structure? Well, in this particular case, this is very simple, because this is really an open subset of this linear space. Why is that true? Well, first of all, there is a natural, we can identify the linear space of n by n matrices with real entries with r to the n squared by using matrix entries. And then the determinant map from here to R is a continuous, it's really polynomial in the matrix entries, and therefore it's continuous. Now GLR is really defined as those matrices whose determinant is non-zero. In other words, it may be viewed as the pre-image for the determinant map of the set of real numbers with 0 excluded. Now this is an open subset in R. So we have a continuous map, and we have the pre-image of an open subset, and that's an open subset. So this is open in M and R, which was isomorphic to R n squared. So it's an open subset of Euclidean space, and this has a natural manifold structure, which corresponds to the submanifold structure related to the manifold structure here. So GLR open implies that it is a manifold. It's an n squared dimensional manifold. What can we say about the coordinate patches of this manifold? Well, it's an open subset of a linear space, so what we can do is we can use the global coordinates of the linear space, restrict those to the open subset, and then we have the coordinates of that manifold. We have a global set of coordinates. So let's psi ij be the map from M and R, from the all matrices to R, mapping a matrix A to its ij entry. Then this obviously is a global set. Well, here it's a set of linear coordinates. So in particular, this is a global coordinate chart for M and R, with values in R n squared, if you like. And if we restrict those to GL and R, then this is a set of global coordinates. So if we want to show that that GLR is a Lie group, then what we should do is we should show that the multiplication map of matrices is smooth in terms of these coordinates, and that the same thing holds for the inversion map. So, if we have two matrices A and B, say, of the general linear group, or we could take any pair of matrices, then of course, the ij coordinate of the product is given by the familiar matrix multiplication map. And that means we can also write this as, take the product mu of A and B, look at what it is for the ij coordinate, and then this is an expression in terms of the coordinates of A and the coordinates of B, which is obviously smooth. And therefore this is a smooth map. So this shows really that mu is smooth. Now what about the inversion? For the inversion of a matrix, which is really the inverse of the matrix, we have a formula which is known as Cramer's rule, which says that you can take the inverse by inverting the determinant of A, and then by multiplying with the co-matrix. And the co-matrix is obtained by refactoring the matrix in the diagonal, then take all the principal minors, then put minus signs in front of it in an appropriate way. So if you look at these operations, then it is immediately clear that this is smooth in terms of the coordinates. If you want to see more details, please have a look at the lecture notes. So clearly now, this is a Lie group. And we have a subgroup consisting of the matrices of determinant 1. And what we're going to do after the break is we are going to show that this is a submanifold, and it's a subgroup, and therefore it's a Lie group at the same time. But let's first have this break. And I propose to... Oh, I'm very sorry. I'm used to start at the hour, so I have the feeling that I should have finished the first half of this lecture by now, but I really started 1/4 past, so I still have a few minutes. So let's finish the first part of the lecture. Sorry about this. By the way, is everything clear so far? Yeah? So I now want to address the group SLNR, which is the group of invertible matrices with determinant equal to 1. My claim is this is a Lie group. What is the strategy to prove this? The strategy is to show first of all that it is a subgroup of GOMR, and then secondly that it is a smooth submanifold. Of GLNR. Now I can be very brief about the first item, that it is a subgroup is really completely evident from the multiplicative property of the determinant. But I could state this in a way that is a bit more fancy. So let's do that anyway. 1, 2. 1. The determinant map from GLNR to R is a group homomorphism. And SLNR is defined as the kernel. Don't you mean R star? R star, thank you. With the multiplication and the identity element. And so that means that SLNR is the kernel of this determinant. And the kernel of a group homomorphism is a subgroup. In fact, it's a normal subgroup. SLNR, so in this way we immediately see that SLNR is a normal subgroup of GLNR. So So this implies SLNR is a normal subgroup. So the second issue is the issue whether SLNR is a submanifold. So is SLNR a submanifold? So what was the meaning of being a submanifold? Well, I'll use the following definition. Something is a submanifold, a subset of a manifold is a submanifold if it is a submanifold at each of its points. It is a submanifold at a particular point if around that point there is a chart of the full manifold such that the subset in that chart becomes straightened out to a linear subspace. So let's write this down in pictures. So we are with issue 2. The question is whether SLNR is a submanifold of GONR. What does this mean? This means that at each point, say, at each of its points, but let's phrase this a bit more general. So let's call this H, and let's call B, and I will give an argumentation that will really be a statement about the general Lie group G and the subgroup H. Now what does it mean that H is a submanifold of G? This is equivalent to saying that at every H of H should be is a submanifold of G at the point H. And what does that mean? Well, let's draw a picture. So here we have a mental picture of our Lie group G, and here we have a mental picture of our Lie group H. And what I want is that at every point H of the group H, it should be possible to find a chart, meaning an open neighborhood, and the diffeomorphism chi to an open neighborhood in Rn, the dimension, so n being the dimension of G. So let's say that H is going to be of dimension m. Then Rn can be split as a direct sum of Rm and Rn minus n. And the requirement of this chart chi is that the image of the intersection of H with U is straightened out to the intersection of the image of chi of U with Rm. So in other words, so what we should have, there should be a chart consisting of the U and the chi, such that the image of U intersected with H should be equal to the image of U intersected with Rn viewed as a linear subspace of Rn. In other words, we bring this thing on a kind of standard form. It should be possible to use a chart to bring this subset in the neighborhood of H on that standard form of a linear subspace. This was the definition of a submanifold. And now, clearly this definition is rather complicated, so it would be quite difficult to do this in general if we didn't have general principles to decide when subsets are submanifolds. One such general principle is the subversion principle. which says that every submersion locally has a particular form. Let me see. So after the break, we will show that, so after the break, we will do a couple of things. First of all, we will show that the tangent map at the identity element of the determinant map is surjective. Then by the subversion principle, this will show that SLNR, which really is the fiber of this determinant map, about 1, is a submanifold at the identity. And then secondly, we will use homogeneity to show that SLNR is a submanifold of GLNR at each of its points. But this will be done after the break. We'll have a break now of precisely 15 minutes.